Welcome to the session on air quality microsensors for Earth observations, an EPICS-in-IEEE initiative. My name is Pomozo Bebwele. Professor Sarah Psina and I both volunteered to work on this EPICS-in-IEEE initiative in Pretoria, South Africa. I worked on the project as an undergraduate electronic engineering student in my final year of the bachelor's degree program. Wireless sensor networks have recently gained much attention in the field of Earth observation because when compared with conventional wired communication networks, wireless sensor networks do not have physical infrastructure that restricts the topology. Traditionally, air quality monitoring systems are limited to centralized or static sites, and thus obtain a limited amount of data for estimation of hazardous air pollutants. Following the success of the EPICS-in-IEEE pilot in 2009-2010, yet another project was initiated at the University of Pretoria, South Africa, in 2012. The project was limited to measurements of ambient air quality parameters with reference to the South African National Environment Management Air Quality Act specifications, measuring gas concentrations above the Air Quality Act ambient air threshold levels. The IEEE was represented through the IEEE South Africa section. The project was also supported and guided by the EPICS-in-IEEE Committee, IEEE Educational Activities Board, IEEE Ad Hoc Committee on Humanitarian Activities, and through the IEEE South Africa, the National Science and Technology Forum was engaged. The project development team that was involved in the design comprised a senior undergraduate student at the University of Pretoria and a group of 8 grade 11 secondary school learners from St. Alban's College, a boys' high school situated in Pretoria, South Africa. While the undergraduate final year student designed an analogous system by first principles, the secondary school learners used educational air quality microsensor off-the-shelf components. The secondary school learners used commercial off-the-shelf or COTS components to construct a board-level design. The board-level development, which was somewhat analogous to the EPICS-in-IEEE pilot that was completed at Drexel College in Philadelphia, United States, initially aimed to replicate the approach and in this way scale the Drexel effort. Eventually, only the principle of wireless sensor nodes was replicated, allowing learners and students for some level of independent study. The approach by the high school students was intended to allow learners to construct a quick solution to the work done by the partner undergraduate final year student. The 8 learners were split into 2 groups to form a 4-group students each. The first group was comprised of Yu Wen Wu, Hanno Moire, Jonathan Reinders, and Alex Diconi. The second group was comprised of Rama Rapalarani, Machaba Sateche, Struan Kori, and Ki Jan Slinger Jobet. The air quality monitoring kits developed would also serve as an educational or teaching tools for improving the public understanding of air quality. From the University of Pretoria, the student lead was Pomozo Bebwele, supported by Professor Sarah Psina. Sarah served in numerous senior IEEE capacities in 2012, but most significantly, also an EPICS-in-IEEE Global Initiative co-founder. A postgraduate university student, Joe Valiarampeth, supported discussions at the secondary school. The two groups that were formed had different roles as follows. On the first group, Alex de Koning was responsible for Eagle and developing printed circuit board layouts relating to the project. He also worked on testing the sensors and gathering data. Yu Wen-Wu, Hanno Moire, and Jonathan Reinders were responsible for software development as well as working on the interface between the hardware and Google Cloud. On the second group, Struan Curry and Gijan Slinger Joubert were responsible for all the sensors and designing any hardware relating to the sensors. Rama Rapalarani and Machaba Satehe were responsible for power supply and related electronics and cell phone interface. To initiate the partnership between the University of Pretoria and the St. Alban's College for the 2012 project, a first meeting was held at the St. Alban's College where the undergraduate final year student did a presentation to the learners. Professor Sina provided a general talk on IEEE's tagline, Advancing Technology for Humanity. After this presentation, follow-up meetings were held to complete the project. In 2012, 7 meetings were held in total. Numerous email exchanges also took place. The 7 meetings that were held in 2012 are detailed in this slide. The figure shows rough notes from a follow-up discussion following the first meeting at the St. Alban's College. These discussions are also available on the Facebook group that was created for this project. The Facebook group includes IEEE volunteers and members who can be seen as friends or fans of the project. Some 24 members are active via the Facebook group. The figure shows other rough notes from a follow-up discussion following the first meeting at the St. Alban's College. The discussion was held interactively and engaged high school and university learners in an active manner. The particular discussion was facilitated by Professor Sina. As highlighted earlier, these discussions are also available on the Facebook group that was created for this project. The figures show rough notes during the third meeting at the St. Alban's College. The Facebook group that was created for this project is provided here. Please join. This slide shows a snapshot of the Facebook group that was created for this project. These photos were taken when the learners were working on the project at the school. This photo was taken at the University of Pretoria, in the new Engineering 3 lab. Secondary school learners worked on the final integration and a project demonstration. A group photo for the particular EPICS-in-IEEE project. Looking into what the undergraduate final year student designed, the figure shows the low-power wireless sensor node that was designed by first principles. The node consists of the gas sensors, a microcontroller unit, a secure digital card, and a global system for mobile communication, general packet radio service, GSM GPRS module, as the main components of the node. The PCB measurements are 150 by 150 millimeters, designed on FR4 PCB material. The figure shows the graph that shows the expected battery life of the wireless sensor node. The battery life of a node was investigated to address a design challenge of the project. The primary engineering challenge was the low power management of a node. Specific characteristics of the nodes, such as power consumption, were considered because power consumption of an individual node differs depending on its type, and this represents a challenge when ways are sought to maximize the node's lifetime. The node battery life was found to be 165 minutes, about 2 hours 45 minutes. This low wireless sensor node's battery life was due to the GSM GPRS modules that were used. These modules require a 4.2 volt power supply that can sink 2 amperes of current when transmitting. The minimum current consumed by these modules is 1.2 milliampere in sleep mode. The GSM GPRS modules consume a considerably higher current than all the components on the node PCB. The figure shows a fully built sensor sync PCB which was designed to act as a gateway to the data terminal. The sensor sync design method was to replicate the wireless sensor node's design, with the exception of a power unit. The sensor sync was powered by a USB connection between the sensor sync and the data terminal. No design was required for the data terminal. Only the graphical user interface and the database for the user to interact with the data terminal. A standard PC running on a 32-bit system was used to implement a data terminal. Looking into what the learners designed, off-the-shelf components such as the carbon dioxide gas sensor, mini Android 4.0 Google TV player, Yo-Yo interface for the Yo-Yo, the Galaxy S2 smartphone Android phone, smoke detector, micro SD cards, and other electronic components were used. The processing of the data was done at a remote location that also served as the central processing node of the sensors. These smartphone-based nodes were also enabled for Global Positioning System, GPS, location tracking. This allowed the learners to display the results visually using Google Maps. Contrary to the university students' effort, the pre-university learners selected a simpler and readily available carbon dioxide sensor. The sensor has 3 data pins that give the measured carbon dioxide in parts per million, a controlled signal, and a trouble signal. A controlled signal indicates the status of the carbon dioxide threshold levels, and a trouble signal indicates when the sensor is faulty or fully functional. The carbon dioxide gas sensor's power supply is 5.0 plus minus 0.2 volt DC regulated. The project was divided into subsections to allow each learner to be responsible for his own section. The system block diagram of the CORDS-based air quality sensing system is presented in this slide. Little to no advice was given to learners relating to the specifications of each section. The students had to do their own research on what is available in their selected areas and had to report back to the whole group. From their feedback, a more detailed system design was formulated. To investigate the use of renewable energy, the students also researched the option of using the iSense solar power harvesting system as a power management unit. The figure in this slide shows the iSense solar power harvesting system that can produce a 5-volt supply using a combination of photovoltaic cells and/or rechargeable batteries. These photos were taken at the University of Pretoria in the Engineering 3 lab when working on the project demonstration and final integration. The left figure shows the Android yo-yo board, which was used as an interface between the microsensors and other electronic hardware, including the smartphone which was used. The yo-yo interface consists of 8 analog to digital converters and various peripherals, as well as the capability to produce a regulated 3.3 volt and 5 volt supply from a 5 volt to 15 volt source. The yo-yo device communicates with the smartphone using either a USB connection or Bluetooth connection. As seen in the figure on the right, the students were able to experiment both communication methods. All the yo-yo functionality was controlled by a simple API that is freely available online. An open source online forum that gives assistance on any yo-yo problems makes this interface also ideal. This slide presents the budget for the first principle approach. Selected project supplies or direct costs for the first principle approach was about 14,891 rands, approximately 2,000 US dollars. This slide presents the budget for the off-the-shelf approach. Selected project supplies or direct costs for the off-the-shelf approach was about 11,960 rands, approximately 1,500 US dollars. Now discussing the future plans. A new edition of the project may proceed in future by starting with 10 working nodes ready for testing in early 2013. The possible integration with Google Maps using GPS capability to the nodes is anticipated. Another intention is to investigate adding other sensors and scaling to include other schools in the area. A paper relating to the work in this project has been submitted for peer review for the IEEE Global Humanitarian Technology Conference. Other future plans include EPICS-in-IEEE presentations at primary and secondary schools in 2013, identifying some 10 schools to become air-quality testing stations, and to improve public understanding of air quality. As a positive progress into the future plans, Modiri Technical High School is already identified as a historically disadvantaged school that could benefit from this project. The school is in Mamelodi, Pretoria, Gauteng, South Africa. The estimated impacts include improving the public understanding of air quality and encouraging learners to have a better perception of engineering. Expanding the community service through Modiri Technical High School and to use other schools as locations for the testing nodes. Thank you for your interest and partaking in this presentation.